right, this last part of the chapter, we're going to look at some equations that we looked at in Intro Chem, and maybe one or two that's a little bit new, and then look at a couple of more stoichiometry questions. So first, combustion reactions. You might remember these. We take a hydrocarbon, react them with oxygen. The two products that you always want to remember are carbon dioxide and water, but water coming out in the gas phase because it's hot. Sometimes you'll see heat written in, sometimes you'll see a triangle for heat, but you're past the boiling point, so water comes out as a gas. Now to balance these, like we talked about with the balancing equations for part 1 of chapter 4, oxygen we're going to save to the end, but we can do carbon first. There's 5 carbons in C5H12, so we're going to make 5 CO2s. There are 12 hydrogens in the hydrocarbon on the reactant side, so the multiple of 2 to get me to 12 means a 6 in front of the H2O. And then when I look at my oxygens, I've got 10 in the carbon dioxide plus another 6 in the water, so 16 total. Multiple of 2 to get me to 16 is an 8. So an 8 goes in front of the oxygen on the reactant side. In the next one, I've got C10H22. So again, we're going to make carbon dioxide and H2O gas phase. When I look at my carbon first, I've got 10 in the hydrocarbon. So 10 goes right in front of CO2 on the product side. 22 hydrogens, divide that by 2, means 11 in front of the water. Now, whenever you have an odd number of waters, you're going to have an odd number of oxygens. So there's 2 ways to go about balancing this. When I look at oxygen on the product side, in the CO2, 2 times 10 is 20, plus 11 in the water, so 20 plus 11 is 31. So on the reactant side, the multiple of 2 to get me to 31, since that's not a whole number, I can leave it as a fraction, so 31 divided by 2. If, however, you want whole numbers, you're going to multiply your hydrocarbon, C10H22 in this case, with a 2 in front, and then all of your coefficients are just going to end up being multiplied by 2. So on the product side, instead of 10 CO2s, we'll have 20, and instead of 11 H2Os, we'll have 22. All right, so that's an easy way to fix that. So combustion reactions always make CO2 and H2O. Now the next section in the textbook talks about reactions with alkali metals like sodium, potassium, lithium. And when we combine them with halogens like fluorine, chlorine, bromine, or oxygen, they're called combination reactions, and they always form an ionic compound. And that ionic compound is based on the charges. So like sodium with chlorine makes sodium chloride, NaCl plus 1 minus 1. If I had sodium plus oxygen, then in this case we're going to make Na2O because sodium's plus 1, oxygen's negative 2. Now the halogens and oxygen, right, that is part of Hofbrinkel. Those are your 7 diatomic elements. So when they're by themselves in their elemental form, not as ions, they are diatomic. So notice the Na is not diatomic, but the chlorine is, just like oxygen is, even though the sodium isn't. If it's one of those 7, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, Hofbrinkel, right, then you want to make them as diatomics. So when I look at my sodium and oxygen example, because I have 2 oxygens, and that would be in the gas phase on the reactant side, I'm going to make 2 sodium oxide solids on the product side. That gives me a total of 4 sodiums, so to balance a 4 in front of the sodium on the reactant side. So what happens here is this is a redox reaction. The elements that start out on the reactant side have no charge. They're atoms or diatomic molecules in the case of Hofbrinkel. And then on the product side, you form an ionic compound by balancing out the charges of the 2 ions that are formed. Now, the other thing that can happen with alkali metals, they're highly reactive. So they can react with water, and that would be a single displacement reaction. This is how they got their name alkali. Alkali means base, right? Hydroxide is our base. When they react with water, they make hydroxides. So the sodium and water, the hydrogen comes out as H2, again, part of Hofbrinkel, and the sodium goes with the hydroxide. So another example here of an alkali metal with water, if we were looking at potassium with H2O, you always want to predict that you would form the metal hydroxide, in this case potassium hydroxide. Potassium's +1, hydroxide's -1, so just KOH. The hydrogen comes out as a gas, H2. And then to balance, right, the potassium looks okay, the oxygen looks okay, but the hydrogen not okay. I've got 2 on the reactant side and 3 on the product side. I know I'm working in a multiple of 2 on the reactant side, so if I went with 4, then, or well, a total of 4, so 2 in front of water, I'd have 2 hydrogens in the H2. If I multiply the KOH by 2, that would give me my 4 hydrogens. Then 2 in front of the water also matches my 4 hydrogens. The 2 oxygens are also balanced, and now I've got a balanced equation except potassium. I also need 2 of those. All right, so that is alkali metals with either an element, an oxygen, or a halogen, or reacting with water. So on the last page, a couple more stoichiometry questions. It says solid potassium metal combines with oxygen gas to form potassium oxide. What would be the percent yield if 82.5 grams, whoops, that's a typo, grams of potassium oxide was formed from reacting 75 grams of potassium with 75 grams of oxygen? So because we just learned how to do that equation, we're going to come up with it ourselves. We have solid potassium metal reacting with oxygen, right, Partohoff-Frankel, so O2, to form potassium with a +1, oxide with a -2. So it should be K2O, and that would be a solid. Now the oxygen has to be diatomic. There's 2 on the reactant side, so I need 2 on the product side. And now there's 4 potassium, so 4 in front of the K on the reactant side. And it says 82.5 grams of the potassium oxide was formed. That's my actual yield. And I reacted 75 grams of potassium with 75 grams of oxygen. So I have a limiting reactant percent yield question. The mass of the product, the 82.5 grams, that's going to be my actual yield that I'll plug into my percent yield calculation, which means I need to figure out what my theoretical yield is. So that'll be my B. So first thing I'm going to do is I'm going to take my 75 grams of potassium. Molar mass, 1 mole of potassium is 39.10 grams. The mole-to-mole ratio, for every 4 moles of potassium, I make 2 moles of potassium oxide. And then for the molar mass of the potassium oxide, I'm going to take that 39.1 twice, and then the oxygen, and I get a molar mass of 94.20 grams. So 75 divided by 39.1 times 2 divided by 4, and then times 94.20, I get 90.3 grams of K2O. All right, now second calculation, I've got 75 grams of O2. 1 mole of O2 is 32 grams. Mole ratio here is 1 mole of O2 makes 2 moles of K2O. Then the molar mass is the same, 94.20 grams per mole for the potassium oxide. All right, so 75 divided by 32 times 2 times 94.20, and I get 442 grams of K2O. So that means the most I could make would be the 90.3 grams, because my potassium would be my limiting reactant. It would run out first. So I have my theoretical yield now, and I have the percent yields that was given to me. I'm sorry, the actual yield. So if I want to figure out my percent yield, I take the 82.5 gram actually made, divided by the 90.3 grams that theoretically should have been made, and that will give me my percent yield, which is 91.4%. All right. So the only thing that's different here from the questions we did on the previous video with limiting reactant and percent yield, it's just that in this example we had to come up with the equation ourselves because we now know how to do that. So same thing is going to happen with problem number 2. What mass of carbon dioxide would be generated from the combustion of 15 gallons of octane? So we're going to have C8H18 reacting with oxygen. We're going to make 8 carbon dioxides, and we're going to make 9 H2Os. All right, so then when I look at my oxygen, I've got 16 oxygens in the CO2 plus another 9. So 16 plus 9 is 25. So we can leave it as a fraction, 25 over 2 for the oxygen. So what mass of carbon dioxide could be formed from 15 gallons of the octane? All right, and the density there is given. So we start, this is only an A to B. It's not limiting reactant. Nothing is given about the oxygen, so we assume that it's present in excess. So I have 15 gallons of C8H18. What's given to me here, this is a conversion factor you want to remember. 1 gallon is 3.785 liters. All right. Then 1 liter is 1,000 milliliters. And the reason why I'm going there is because I'm going to use the density of the octane to get to grams, so 0.703 grams per milliliter. Now that I have mass, I can use molar mass. So 8 carbons at 12.01 apiece and 18 hydrogens at 1.01 apiece. I get a molar mass of 114.26. All right, so let me just get this answer first because I'm kind of running out of space. All right, so I'll take my 15 gallons times 3.785 to get liters, times 1,000 to get milliliters, times 0.703 to get grams, then divided by 114.26 to get moles. So I have 349, I'm going to worry about sig figs later, moles of C8H18. Now to finish this out, I have 349 moles C8H18. Mole ratio, for every 1 mole of C8H18, I make 8 moles of CO2, and then to get to grams, 44.01 grams is the molar mass of the carbon dioxide. So it's going to be a big number. All right, so I get 1,22987 grams of CO2. But going back to what was given in the question, I can only have 2 significant figures. So we're going to round this to 1, 2, and then replace 2,987 with zeros. But as we kind of talked about before, scientific notation is really the proper way to do this. So 1.2, moving the decimal 1, 2, 3, 4, 5 spots to the left, so positive 5. 1.2 times 10 to the 5 grams of carbon dioxide. All right, so if you're given, if we're talking about stoichiometry, what we've talked about so far is the mole-to-mole ratio is always the center step. If you want mass, molar mass from the periodic table is what you need. If you have a volume of a pure liquid, then density will take you to mass first, and then you'll do molar mass to get to moles. All right, so that finishes up the notes for chapter 4.